Welcome learners. In today's lecture, we are going to look into the response of first order circuits, the first order circuits also known as RL and RC circuits. So till now we have learned about the working principle of inductors and capacitors. We know that these both circuit elements behave as an energy storage device, where inductor is storing the energy in the form of magnetic field and capacitor stores energy in the form of electric field. We also talked about their terminal behavior, where we looked into the governing equations for the voltages and currents flowing through these inductors. Now in this lecture and the upcoming lectures, we are in a position to understand how the voltages and currents arise when the energy is released or acquired by these circuit elements due to an abrupt change in the sources. So now in this lecture we are going to understand how the voltages and current arise due to energy released or acquired by the circuit elements inductor or capacitor because of abrupt changes or transitioning from point A to point B of sources. So this is the goal of this chapter. And another thing that we are going to focus that makes this RL and RC circuit work is that we are going to have a combination of a source with a resistor followed by either an inductor or a capacitor. So we will have something like a source followed by a resistor and inductor, or we are going to have a source followed by a resistor and a capacitor. We cannot have resistor or inductor connected together in this configuration. So the first order circuits or the RL or RC circuits are going to be analyzed independently, but the inductor and capacitor are not to be connected together, and this is the identification of RL and RC circuit. So this becomes your RL and this becomes your RC circuit. So in order to summarize this lecture and the forthcoming lectures, we can say that the lectures are distributed into 3 phases. So those phases being, in the first phase we are going to look into the current and voltages that arise in the stored elements, stored elements being our inductor or capacitor, when the source is suddenly or abruptly removed from the circuit. So in the first phase we are going to look at the behavior of the currents and voltages for the stored elements inductor and capacitor when the scenario is such that the source is suddenly removed from the circuit, and this type of behavior is known as the natural response of RL or RC circuit. So this is the first scenario, and what happens is that we are only left with the circuit that will be of this formation. So either when the source is removed, we will be just left with our inductor or a resistor with the current flowing through it, I of t, or we will be left with a capacitor and a resistor with a respective voltage. So the first phase of the discussion will be what happens to the voltages and currents when a sudden change or the source gets disconnected and we are only left with either a resistor or an inductor or a resistor or capacitor. And this form is known as the natural response of RL or RC circuit. In the second phase, we are again going to look into the current and voltage arise or behavior for the stored elements. Again, in the storage elements, this is inductor or capacitor, but in this time the sudden application of source is available. Sudden application of source is made, which means that the inductor and capacitor start to acquire energy. So in this context, this kind of formation will be known as the step response of the system, the step response of RL or RC circuit. So this is going to be the step response of the system. In the context of acquiring energy, we can also say that the natural response will basically going to release energy, as it is clear from these two images for the first case. So in the first case, or in the first phase, we are going to look at the system where we suddenly remove the source and we are left with only inductor, resistor or a capacitor resistor, and thus the inductor or capacitor is going to release energy. This form of configuration or the analysis based on these configurations are known as the natural responses of the system. In the second phase, we are going to have the circuit elements inductor or capacitor. So we can say that we have this inductor and resistor combination and RL, and then we have this capacitor and resistor combination RC, and we suddenly apply a source to this. So if we suddenly apply a source to this, then what is going to be the behavior of current and voltage? And this kind of system is known as the step response, where the inductor and capacitor will now acquire the energy from the additional source. And in the third and final phase of the discussion on this lecture and the forthcoming lectures, we are going to see the generic modeling and equation of systems to solve the RL and RC circuits when abrupt change happens in a complete system. So we are going to look at the general methods, and we are going to develop or find the RL and RC responses due to abrupt changes in the sources. In order to solve the general equation, we are going to use the assistance of Thevenin and Norton equivalent circuits, which means we can have four possible configurations. The first being, we can have a VThevenin with an RThevenin connected to an inductor. So this is our VThevenin, this is RThevenin, and this is an inductor. So this is for the RL combination. We can have the Norton equivalent as well with the inductor. So we will have the Norton equivalent as well, and same goes for the capacitor. We will have a voltage source with the RThevenin, and then we will have a capacitor. So this is RThevenin, VThevenin and capacitor, and we can have the Norton and its equivalent with the capacitor as well. So we will have RThevenin and then we have IThevenin. So these are the four combinations that we can use to basically find a generic solution to the RL and RC circuits. Another thing to remember is that these circuits RL and RC are also known as first order circuits, as we can see from the heading of this or the title of this chapter, that these are also known as the first order circuits. So obviously, why they are called first order circuits? So we know that RL and RC are governed by their mathematical expressions for the rate of change of current and the rate of change of voltage. So for inductor, if you want to find the voltage across it, it is going to be V equals to L di by dt, and for the capacitor, the current across is C dV by dt. And here you can see that in both the equations we have a first order derivative. So hence this first order differential equations or derivative is basically the reason that RL and RC are also known as first order circuits. So whenever we hear these terms, first order circuits or RL and RC, so we are going to analyze them based on the principles that we are going to study today in order to understand how the voltages and currents arise when the elements are getting charged or they are releasing energy. So now let us begin the analysis of the natural response of an RL circuit and see how we can go about this. So now let us discuss the natural response of RL circuit. So in order to understand the natural response of an RL circuit, we need to remember that RL circuit is analyzed when we are only left with an inductor and a resistor, and hence the configuration will be such. So the current is flowing, and this happens when we suddenly remove the sources DC or AC. So whenever there is a sudden remove of source, we are left with only an R and L combination, and thus we want to know what is the behavior of the voltage and current that arise by the release of the energy from the inductor. So we basically want to understand the expressions for the current and voltages in the RL circuit, and the removal of the DC source basically gives us the natural response. So in order to understand this, we begin with a very basic configuration. So let us consider we have a current source. It is connected to an arbitrary resistor R0, and then we have a switch connected to an inductor and a resistor next to it. So this is your R, this is your L, and here the switch is at t is equal to 0. T is equal to 0 being an arbitrary value. Obviously the voltage appearing across inductor will be VL, and the same will appear across resistor. We call this as VR. The current is flowing in this direction. So this is a simple circuit to understand the natural response of an RL circuit. Again, in this circuit we have a constant or independent DC source. Let us say it is of 1 amps connected to an resistor R0, and then we have a switch which is going to open at t is equal to 0, which means the switch is currently closed when t is less than equal to 0. And then we have the inductor and resistor to the right side of the switch. So let us do the analysis on this circuit. So we assume that we have an independent current source. So we have an independent current source of, let us say, 1 amps, and we say that the switch is closed. Closed means when the time is less than 0 for a long time. So switch is closed for a long time. Now this term long time is very important, and we are going to understand this. Long time is explained in two ways. So the first thing is, long time means that the system has been closed or the system has elapsed for 5 tau, tau be the time constant. So this is the first understanding of the long time. What is the 5 tau or time constant? We are going to talk about it shortly. Another meaning to understand the long time is that the system has achieved a steady state condition. Steady state condition. So steady state condition means that the voltages and currents have reached their final value, which means that if the switch has been closed for a longer time, a constant flow of current and voltage is going to appear across all the circuit elements, where the circuit elements being R0, L and R, which means the long time means, the first meaning that we are going to go with, that the system has achieved a constant value for whatever the source we have, in this case a current source, and the voltages that are going to appear based on this current source. And the second thing long time means is that the system or the circuit has elapsed for 5 tau, or tau meaning be the time constant. So what is this time constant? We are going to talk about it shortly. Currently we are focusing on the steady state condition, that long time means the system has acquired constant values. Since the constant source is now appearing on all of the circuit elements, so we know by principle that if there is a constant flow of current, then the voltage becomes equal to 0 in case of the inductor. This means that the current will only go through the path of inductor from here, and it is going to avoid the path of the resistance, which is at R0 and R. Thus, this inductor receiving a constant current will then behave as a short circuit, as seen over here. So when a constant flow of current is given because of the long time of switch being closed, the inductor is going to behave as a short circuit, which means that the voltage appearing will be 0 volts. So this is the first condition that we have noted from this graph. Now let us move onward with our analysis and now see what happens when the switch gets open. So now we are opening the switch, or the switch gets opened, which means our time has now reached at the value of 0, and we say that it is 0 or greater than equal to 0 or greater than 0. So now when the time becomes greater than 0, we can now do the RL analysis on the circuit. And why we say this? Because when time equals to 0, the switch gets opened, we are left with this configuration where we have now an inductor followed by the resistor. So this is L, this is R, and the current IS, which was previously flowing through it, making this as a DC connection, is now going to appear on this inductor as a whole. So this is our I of S, and the polarities are going to be as such. So this is the current that is now going to appear, and we can see that since there is no voltage source available, the inductor is not going to behave as it normally does, which means that when the current is going to flow, the magnetic field is going to be produced around it, and thus an induced voltage is going to appear as well. So now when the time has reached 0, or we say it is equal to or greater than 0, we can do the RL analysis, and we can do this because we know that for the RL analysis our circuit should have no source and only element available should be L and R. So another thing to remember is that the current over here, IS, is going to be represented as I0 plus. Now what is this I0 plus? We are going to look into this as well, but at this moment consider that I0 plus is the immediate current which is available as soon as the switch gets opened. So now let us do the analysis on this RL circuit in terms of finding the or deriving the expressions for the arising voltages and current. So now we want to know what is going to be the expression when we have this RL circuit in front of us, especially the voltages and currents. So now let us derive the expression for current and voltages. So expression for current, and similarly it will follow for the voltage as well. So if we look at this circuit, the RL circuit that we have over here, so in order to find the current, we can simply apply the KVL on this. So if we apply KVL on this loop, we can say that voltage at the inductor plus voltage at the resistor equals to 0. The voltage at the inductor is L is equal to di by dt, plus voltage is the Ohm's law, IR equals to 0. Let us do some algebraic manipulation to reach a value for the change of current dt. So I can write it as di by dt, and I can move this minus I by RL. Now in order to get rid of t, I'm going to multiply it by dt on both sides, so it gets cancelled. Again, since I'm interested in finding currents, I'll bring I back to the denominator, and my expression will be R by negative R by L into dt. Now we know that in order to find the current we need to integrate this equation. So now we are going to integrate this equation, and in integration I'm going to change the variables of I and t. So I will be changed to x and t will be changed to y. So in order to keep the nomenclature of integration, so I can say my integration will be now in terms of dx by x equals to minus r by l, and dy, r by l being the constant. And what about the limits? So I will apply the current from t naught, that is the initial condition, from time 0 to a maximum value of I of t. Similarly for y I can go from 0 to t. So these are my limits, keeping in mind that I of t is basically t naught is the value at time instance of 0, and I of t is the any time period, let's say, of t. And we also should know that t naught is at 0 instance. So these are the limits that we have defined. Let us use this slide. So now let us proceed by simplifying the integration. So the integration and the limits, if I put, so 1 by x integrate becomes natural log of x. So I'm going to say ln x, where x will be I of t minus I t naught, and then on the other side we have negative r by l. You integrate dy with an integral, so you just get the value of t and you put the limits 0 to t. So this natural log, when you are getting a subtraction by principal, changes into a fraction, so it will be I of t divided by I t naught, and on the other side I will have r by l, and t just remains t as the value it is. And then I can move this I naught to the other side, so I will have a natural log I of t equals to I t naught minus r by l into t. So in order to cancel the natural log, we have a property that if you multiply an exponential and with a natural log, you can cancel it and the power of exponential becomes x. So you multiply this with exponential and you multiply this with exponential. So these two will be cancelled out. I'll be left with I of t equals to I t naught, and the exponential takes the value of minus r by l into t. So now I have this expression, and I can further simplify by putting the value of t naught, which is 0. So then I of t becomes I of 0 e raised to power minus r by l into t. So now this is the expression that I am getting, expression number 1, for the current that is going to be varied when we are having a response of an RL circuit, where the RL circuit is just an inductor and resistor, where the inductor is releasing the energy. And if we logically think about it, we can see from the equation and this circuit as well that when the inductor is releasing its energy, finally it should have a value of 0. And we are also seeing this from the equation as well, that this exponential is basically a decaying function, and r and l is controlling the rate of decay. So it should go to, when the value or time reaches infinity, all the energy stored in the inductor will come to 0, and thus the current will be 0, and same goes for the voltage as well. So let us look into this equation and see whether our logic is right or not. So another thing we can do is we come back to this I 0 of, or I of 0. So we remember that when we were talking about inductors, we talked about an important condition of inductor, that inductor, whenever we are working with inductors, the abrupt or sudden change of current is not allowed. So we avoid this di by dt, because if we do so, the voltage goes towards infinity, and we don't want this condition. So in order to avoid this condition, we use a terminology, or we use equation, that the initial current I0 plus equals 0 negative, which is equal to I naught. So here, what are these terms and how we are taking this, we'll talk about it. So this is the current available, current immediately available after switching Which switching? So this is the switching that we talk about at t is equal to 0. So the moment that we open the switch at t is equal to 0, what is the current that is going to appear? In order to avoid this abrupt change in time, we call or represent this by as I0 plus, and it is going to be the same value as I0 negative. I0 negatives are current which was initially available, or current immediately, or we say current available before the switch is opened. So you see, we have presented two instances in time where I0 negative is basically the amount of current available in the system before the switch gets open, and I0 plus is the amount of current available immediately when the switch is open, and both of these equations correspond to the value of I0, which means that we are trying to avoid the sudden change because that will lead us to an infinite voltage. Now this means that the current that was available, I0 negative, was what value? So it was the value of 1 amps before the switch was open. So we say that I0 negative is basically the current available when time was less than 0, when the switch was open, which switch was closed for a longer time, and the moment we reach the time instance of t is equal to 0 or greater than 0, we have the value of t is equal to greater than equal to 0. So this is I0 plus, and it is going to have the same amount of current. So if the current was 1 ampere before the switch was open, it is going to remain the same after the switch was open, and this is the condition that we want to apply in order to avoid the voltage reaching infinity. Now you may ask, how can we do this? So this is basically possible by special kinds of power electronic switches called SPST or SPDT. So these switches are, so this immediate change without reaching to infinity is achieved by special switches called make before break connection switches. We might have heard about this SPST. This is single pole single throw or single pole double throw. So these are also these categories of switches: single pole single throw and single pole double throw. And another kind of switches, the power electronics one, that are very fast and doing these kind of switching to avoid voltage reaching infinity, is called as a knife switch. So how a knife switch works? So a knife switch might be, let's say you have a voltage source and then you have connected an inductor and a resistor to it, and this is your complete circuit. Let us say this is position number 1, and here you have position number 2. This is your inductor, this is your capacitor. Let's say if my time is equal to 0, so switch was basically at 1 when time was less than 0. So what is happening, that the voltage is producing the current and the current is moving over here, right? So now when the time becomes equal to 0, the switch is going to be moved from point 1 to point 2, which means that the connection of the voltage source will get severed. So this will now be disconnected when the switch moves to 0. But before doing so, we have to make sure that the current remains the same in this circuit. So if we consider the initial condition when time was less than 0, we know that a constant current was getting applied. Let's say if the voltage was 10 volts, then how much current is going to be appear if the resistor is, let's say, 10 ohm. We know where a constant voltage supply was given, the inductor was acting as a short circuit. So I can remove this and have a short circuit over here. When we talked about the long time, in this case the current comes out to be V by R, which is 1 amps. Now when I connected or moved the switch at time is equal to 0 from point 1 to point 2, which is this point, so the same current is going to appear over here, and this is known as a knife switch. So these are special kind of switches that make the connection before they're breaking them such that the same current appears over here, and we avoid the condition of abrupt changing of current, so that to avoid voltage getting an infinite value. So this is how the switching is happening. So coming back to our discussion with regards to equation 1, we see that equation 1 is going to have this behavior, where after this discussion, so let us put this into a bracket. So from equation number 1, what we can say is our I plus 0 plus equals to I 0 minus, which is going to be I naught, and I naught being in our example 1 amps. So equation 1, so if I start with equation 1 for the current, I can say that my final equation or the behavior of current comes out to be I naught e raised to power minus R by L into T. Now this is the current that we are going to see when we are discussing the RL behavior, and the condition to always write and note it that this is only true when the current is greater than or equal to 0. So this is the equation of current that we are going to have when we are doing the RL analysis of the circuit, and we are always trying to avoid an abrupt change. In that case, we use special kind of switches called the knife switches to get this behavior. Now, as I mentioned that logically the current should go to its 0 because all of the energy is going to be released by the inductor. So let us see graphically how we can plot this equation. So this equation is basically going to be, let's say we have a time scale from 0 to t on the horizontal axis, and the current is available over here. From this equation we see that the current has a maximum value at 0. If you put the value of t equals to 0 over here, you get value of I naught. So then I naught is going to have certain value, and after some time it is going to decay like this. So the exponential over here is basically a decaying function, and we can see that the decay function also depends upon the ratio of R and L. So in the graph, R and L basically gives you the current decay, and normally exponential functions are either increasing or decreasing. Since we have a negative sign with e raised to power RL, so this is a decaying function, and thus our logic is correct that after a certain amount of time the current stored in the inductor is going to fade away and it will reach to a value of 0. Now let us see what is the effect of RLN over the graph. So if we have this graph, what is the effect of, let's say this is my current I naught, and if we keep everything constant, let's say voltage and resistor, and we just change L, so what is going to be the effect on this graph? So if the value of L is large, which means that it can store more current, so it will take more time to release the energy or come back to 0. So if we have a large value of inductance, so the current will take more time to come to a steady state condition, which is at the 0 point over here. And if we have the value of inductance to be small, then obviously the current's initial value will remain the same, but it will take a much quicker time to come back to a steady state condition, where steady state condition being the value or the maximum value. So if we have a small r, or this is for a small l, which means the inductance will store a small amount of current, and the steady state condition meaning that the inductance can reach maximum value, which in this case is 0, quite faster compared to a larger value of L. Now what happens if we have the resistance? So now let us say if we again draw this and see the effect of resistance, keeping all the elements constant, let's say the voltage and inductance is constant, and now what is going to happen to the value of current? So obviously we know that if you have a larger value of resistance, the current will be small, because current will not have a chance to go through it easily. So this means that the current is going to reach a steady state condition quite early for a larger value of resistance, and similarly the value of resistance is less, so the current is going to be stored more, and it is going to take more time to reach the steady state condition, which is the final value over here. So for a small value of R, more current will be available as the initial condition, I naught considered to be the initial condition, and a large value of R will have a quicker delay towards the steady state condition, and steady state condition being the final value, and in this case the final value being 0. So now this equation A is basically the equation that we are going to utilize for finding the changing current when talking about the RL circuits. Now let us come to finding the equations of the respective voltages for R and L for the inductor. So what is going to be the expression for voltage? So for the voltage, we consider the same RL structure. So this is our L, this is R, this is the voltage applied because of the current, and this is the voltage over here. So in order to find the voltage, we just apply the Ohm's law, V equals to IR. We know that the current is I naught e raised to power minus R by L into T multiplied by R. And again, the condition is that in this scenario, T has to be greater than equal to 0 plus. So this is the equation to find the voltage for an RL circuit. Here 0 plus means that it is when the time is equal to or greater than 0. This means the voltage is not going to appear when the time is negative or less than 0. So our condition will be that V0 negative is going to be 0 volts and V0 plus is going to be the value that we have, which is I naught R. So this value. So when time is less than 0, we know that there is going to be a sudden shift in time which will leave voltage to be infinite for the inductor. Thus, we don't consider voltage for time less than 0. We only consider it for time greater than or equal to 0 based on the circuit time that we have considered. So these are the conditions associated for finding the voltage. Again, this plus over here means that we are considering this condition moving towards the steady state and not the initial condition. If we had an I0 negative, this would have been considered as an initial condition. So keep the positive and negative symbols in mind, that what does they mean. Okay, now since we have found the currents and voltages, obviously the next best thing is to find the power. So we know power is equal to voltage into current, or it's a product of voltage into current. We can also write it as I square R. It can also be written as V square by R. So if we write it in terms of I square by R, so power comes out to be I naught square R e raised to power minus 2 R by L into T. Again, this is for T greater than equal to 0 plus. So this is the expression to find for the power, and here the negative sign upon the exponential means that the power is getting dissipated. So in case of RL circuits, the inductor is basically dissipating the power. And finally, we can find the energy of the system because we already have power. So we know energy is integration of power into dt. You just input the values. So the power comes out to be, or the energy comes out to be, half L I naught square multiplied by 1 minus e raised to power minus 2 R by L into T. And again, this is for the condition of greater than equal to 0. Okay, so another thing to note over here when finding the energy of the system is that what happens if the value of T approaches infinity, and what happens if the value of T is less than 0, because this equation is, as you can see, for the condition of equal to or greater than 0. So when T is less than 0, this means we are at the initial condition. Here the energy comes out to be half L I naught square. So this is the same energy of the system that we found for the individual inductor. And similarly, when time reaches to 0, so if you put T is equal to infinity in this equation, you get the same value as well. So this means that when the energy is less than 0, it will have the same value compared to when you reach, or when you have the time when it reaches infinity. So the energy that is dissipated equals to the initial energy stored in the inductor for both of these cases. So this case is when the time is equal to or greater than 0, but when the time equals to 0 for the initial condition, or when the time reaches infinity, we will have this equation, which is just Li square. So this is a point to remember when talking about the energy. So now let us come to the thing that we talked about earlier and we want to discuss, and that is, what is this term long time? So we talked about the long time in terms of the steady state condition, and we know that steady state condition is a technical term to understand that whenever voltages and currents have reached their maximum value or a constant has been achieved, we say that this is the long time of the system. Let us now talk about long time in terms of the 5 time constant or 5 tau and see what is this time constant. So now let us understand the significance of time constant represented by symbol tau. So we have seen in our expressions, for example, for the expression of current, we noted this, that it is equal to I naught e raised to power minus r by L into t, given t is greater than equal to 0. Now this value over here, this minus r by L multiplied by t, this is a very interesting factor, because we know that this r and L is basically causing the current to decay and exponentially in the negative term. So this coefficient of t, which is r by L, if we take the inverse of this, we get something known as the time constant. Inverse of this gives us the time constant represented by tau. So we can say that tau is 1 divided by r by L, which is L by r. So when we are talking about analyzing the natural response of an RL circuit, the time constant is represented by L by R. So this is an important equation to remember. Now what does the time constant mean? Time constant means, or basically this tau, which is an important parameter in the first order circuit, basically tells us that how much time is elapsed such that the system reaches steady state condition. In other terms, it means that if we had this inductor and resistor circuit LR, so how much time the inductor will take to lose or release its energy, which means that how much time it will take to come back to or approximately reach to 0 value or 0 Henry. So this is what it means by tau. So this is another kind of a parameter that helps us in understand the system behavior in order for it to reach its steady state condition. So this means that all the expressions that we have generated for current and voltage can be written in the terms of tau, which means the equation for current can be written as I naught e raised to power minus t by tau for t greater than equal to 0. So this equation I am replacing r by L with tau. Similarly, voltage equation can be written as I naught r e raised to power minus t by tau for t greater than equal to 0 plus. The equation for power can be written as I naught square r e raised to power minus 2 t by tau for t greater than equal to 0 plus, and the energy is now written as half L I naught square 1 minus e raised to power minus 2 by tau for t greater than equal to 0 plus. So these are all the equations that are revisited and rewritten in the form of tau. And now we know that tau is another term that can help us understand that how much time the system will take to release its energy, or how much time the system will take to reach its steady state condition. Okay, so sometimes we can also see the importance of tau in terms of a tabulated form or in terms of its percentage. So normally we represent the system's behavior in terms of integral multiples of tau. Integral multiples of tau, which means we can write the system behavior as 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, and we go till 10 tau. But our concern or our important point is that our system reaches the steady state condition, as we talked about it in the beginning. Steady state condition is reached when we reach the value of 5 time constants or 5 tau. So when we reach the integral multiple of 5 tau constant, what happens is that the total the current which is being drained from the inductor is now, or it becomes almost 2% less than the original value of current, than the original current value. So that's why we consider the systems to have a 5 tau or 5 tau time constant. So whenever a system reaches 5 time constant, we say that the current has almost become 2% less than what its original value was. What it means is, so let us put this into context. If, for example, if this is my current and this is the behavior of the inductor being releasing energy, we know that the behavior will be such that the steady state condition is reached when it reaches the maximum value, which being 0 in this case. So now 2% means that this much of energy has already been released by the inductor, and now we are nearing the steady state, which means that with respect to its original value 2% might be this position, and after this we say that 5 tau has been achieved. So this is the what it means, that 2% less original current than the original value. So original current being I naught at 0, and almost at 5 tau constants 2% of less current is available, which means that energy between 0 and 5 tau has been released. And another way to understand this is if we write it in the form of a tabulation. Let us say if I consider T by tau to be a value of let's say 1, so its integral multiples can be written as T is equal to 1 tau, 2 tau, and so on till 10 tau. So if I write it in such way that let's say T is equal to values of taus, so 1 tau, 2 tau, 3 tau, 4 tau, and 5 tau. I can go beyond till 10 tau, but we are discussing till 5 tau, and let us write the value of the exponentials with regards to this. So for the equation of current we have, and then for 10 tau we can go. So exponential was minus T by tau, which becomes e raised to power minus 1 if you replace T with T by tau, so it is going to be 1, then it comes out to be, so exponential value of exponential is 2.718. you just take the negative of 1, so you might get a value of 0.36. then you take the exponential of 2 tau, then the value will come out to be 0.13. Similarly, you take the value of exponential to be minus 3, then it comes out to be 0.049. then you take the value of minus 4, and it comes out to be 0.01, and hence when you reach the value of 5 you get the value of 0.006. So 0.006, and now you can see that we have almost at 5 tau reached the value of 0, and this is why we say that the system needs to elapse 5 tau or 5 time constants to reach a steady state condition. So that's why we consider this to be a standard for analyzing the RLC circuits. So hopefully this clears the principle of time constant. And sometimes another way to find the tau if the values of R and L are not given is again by the current's graphical expression or graphical representation, that if this is the behavior of current and it is decaying like this, so this is basically I naught e raised to power minus R by L into T, and we need to find where the tau is going to be. So normally at this T equals to 0, you just draw a tangential line, and the point where it connects with the horizontal axis is your tau, and from there on you can see that from this region to this region the steady state condition is going to appear, and the initial value of tau could be calculated from here. Then you can go from tau to 5 tau. So this region will be your transient region. Transient region mean where the energy is getting varied, and after 5 tau, so let's say this point is your steady state region or steady state condition. So finally, whenever we want to know the behavior of the circuit, so the total circuit behavior is going to be the transient behavior plus the steady state behavior. And obviously the transient behavior will be categorized into natural response or it can be step response. But the steady state remains the same because it is the maximum value that we want to achieve or the system want to achieve. In case of RL, it is 0 value for both voltages and currents. And if we want to solve any circuit analysis problem related to the RLL, the steps will be so the steps to solve any circuit related to RL will be, first we need to find the initial condition, which is represented by I naught. It is the same as I0 negative. The second, we find the time constant. In case of inductor, it is 5 tau. And finally we find the steady state condition, which is I of t's equation, which is I naught e raised to power minus r by L into t. Same can be said for voltage, power and energy, the equations that we have seen till now. So this is how we can find the steps needed to solve any electrical circuit involving RL combination. And now we are going to see an example on how to apply these steps to solve this example. Let us look at an example and see how can we apply those steps to solve or figure out the solution to an RL circuit. So in this example, we are given a circuit that is closed for a long time. So this is an important term, a long time, which means we need to first find the initial condition. So the switch is closed for a long time and then it gets opened at t equals to 0. Again, here you can see the symbol. The arrow is in the upward direction. So this means at t is equal to 0, the switch is going to open. And for this circuit, there are 4 unknowns that we need to figure out. The first part A being find the inductor current when t is greater than equal to 0. Second, to find the I naught t for t is greater than equal to 0, where I naught t is moving in the rightmost direction. We need to find the V naught t when t is greater to 0. Again, it is available across the 40 ohm. And in the last part, we need to find the percentage of the total energy stored in the 2 Henry inductor that is dissipated in the 10 ohm resistor. Okay, so let us start solving this and start with the solution to the first one. Obviously, we first need to consider the long time. In case of inductor, we need to find the initial condition because long time is going to give us I0 negative equals to I0 positive, and it is going to give us the initial current over here. So when the current is closed for a long time, which means we have to see when the value of t was less than 0. Again, remember, t is an arbitrary time instance that has been given to us. So when the switch is closed, what happens is for a long time that all the currents or all the sources have reached their constant or maximum value, which means that the DC behavior is being observed. So we can say that DC behavior or a constant behavior is being observed, which means what is going to happen to the circuit. So the current source 20 ampere is going to avoid entering into 0.1 ohm because there is a resistance. So this 20 ampere is not going to enter the 0.1. Since the switch is closed, it is not going to enter the 2 ohm because current is always seeking a path which less resistance. Now as soon as it enters the inductor, since it's a constant supply, this inductor will now become short circuited. So now the whole of the current is going to appear over here. This means that our initial condition for the current is going to be 20 amps, and this is going to be later on our steady state condition as well. So again, the current is going to avoid all the entrance into the resistor and it is just going to take the short circuit path, which means that whole of the current 20 ampere source is going to appear across the 2 Henry inductor because a constant voltage of a constant supply of current as per equation gives you a 0 voltage, which means that your inductor is behaving as a short circuit. So this is our initial current available over here. Now let us come to the condition when t is greater than equal to 0. This means that the switch is now open. Switch is opened. Now when the switch gets opened, what is going to happen? The first thing we need to know that our circuit reduces to just an inductor followed by a resistor, then followed by a resistor, and then we have another resistor, and then we have another resistor. So now we have a 2 Henry inductor with a 2 ohm resistor followed by a 10 ohm and a 40 ohm resistor. Now this is the circuit that we have. The current through the inductor is flowing in the downward direction. The current I naught is from left to right, and we need the voltage across 40 ohm. So now how can we solve this? So the first step was to find the initial condition, which we already did in the form of I naught. Now the second step is to find the time constant, which is basically tau in this case will be L divided by R. So this is the time constant that we want to find. In order to find time constant, we need to simplify the circuit, and we can easily see that these resistors are forming a configuration that can be solved. So we can see that 40 and 10 ohm are parallel, and then they are in series with the 20 ohm. So I can say that 40 is in parallel with 10 ohm, and then whatever the sum answer comes out is going to be in series, which is going to give me my answer. So if we solve this equivalent, it is going to be 40 multiplied by 10 divided by 50, and it comes out to be 400 divided by 50, and then you add the 2 to it, so it is going to be 8 plus 2, and it comes out to be 10 ohm. So the value of the R equivalent, let us call this R equivalent, comes out to be 10 ohm when we solve this circuit. So now we have our circuit that is having only the value of an inductor followed by R equivalent. This is L and this is R equivalent. So now we can easily find the time constant. So here the time constant is L by R, which is 2 Henry divided by 10 ohm, and it comes out to be 0.2 seconds. So this is the time constant that we have. So once we have figured the time constant, now let us find the current. So the current IL of t is basically I naught e raised to power minus R by L multiplied by t, where I naught is the initial current which we found from here, which is basically 20 amps. So it is going to be 20 ampere multiplied by exponential minus R by L. Either you can write R by L, their respective values, that is basically 10 divided by 2 into t, or you can just write it in terms of tau. So if we write it in terms of tau, the final current comes out to be 20 e raised to power minus 5 of t amps, and the condition is very necessary. It is 40 is greater than equal to 0. So this is the current across the inductor that we have figured out. So this concludes the first part. Now let us come to the second part. So the first part is concluded. In the second part, we need to find I naught t when t is greater than equal to 0. Again, I naught t is moving from 10 ohm and entering into the 40 ohm. So in this circuit, I naught, so in order to find I naught, we can simply apply the current division rule. So in order to find I naught of t, we can apply the current divider rule. Here we need to find the current passing through the 40 ohm. So the current divider rule is I naught t is equal to, you need to find the current of at 10 divided by 10 plus 40. So you need to find the current passing through the 40 ohm, which means you have to take the opposite current value of 10 and multiply it with the source I of L with a negative sign. Why there is a negative sign? Because the I of L is in the opposite direction to I naught. So IL is going in the downward, I naught is in the opposite direction. So this comes out to be minus 0.2 into I of L, and I of L is basically 20 e raised to power minus 5. So when you input the value, it is going to be minus 4 e raised to power minus 5t amps, and the condition is greater than 0 plus. So this is I naught t over the 40 ohm resistance. Again, plus is written because we are finding the steady state condition, and this current is not going to be the same for the initial condition. The initial condition was I naught t, here I naught t is not utilized. And finally, let us come to the third part. In part number C, we need to find the voltage V naught t. V naught t is appearing across 40 ohm as shown over here. So this is just an Ohm's law. We already know the I naught which is moving. So V naught t is equal to I naught into R, which is basically minus 4 e raised to power minus 5t multiplied by 40, and it comes out to be minus 160 e raised to power minus 5t volts. Again, condition is greater than 0 plus. So this is an important. So this is the voltage that we have found. And finally, we need to find the amount of total energy stored. So the percentage of the total energy stored in the 2 Henry inductor through the dissipation of the 10 ohm resistor. So obviously we need to first figure out, in order to find energy, we need to know the power associated with this. So the power is basically V square by R. We know that V naught is this equation and R is at 10. So I can write it V naught square divided by 10 ohm. So it comes out to be 2560 e raised to power minus 10t watts, condition being t is greater than or equal to 0 plus. This is, again, you can see our exponential has a negative sign, so this is the dissipated power. And finally, in order to find the energy across the 10 ohm, we are just going to integrate the power across the 10 ohm, which is going to be 0 to t 2560 e raised to power minus 10t dt, and it comes out to be 2560 minus 10, and the integral will be e raised to power minus 10t from 0 to infinity, and then it comes out to be 256 joules. Now we know the power across the 10 ohm and the energy at the 10 ohm. We want to know the total power in the system. So we know that the initial energy of the system, initial energy again means when the time is less than 0, is always going to be equal to half L I naught square. So this comes out to be half. Inductance value was 2 Henry and energy current initially was 20 amps square, so it comes out to be 400 joule. Now in order to find the percentage energy of the system, so we are just going to take the current energy in the 10 ohm, divide by 400 and take the percentage, and it comes out to be 64%. So this is the total amount of energy dissipated in the system, and hence this concludes our solution to this example consisting of 4 parts.